This is problem number 2 on problem set number 5. There will be a problem on the next exam that's just like this problem. This problem deals with the concept of impulse, and I'm going to show you how impulse is related both to the concept of force and to the concept of momentum. I'm just finishing drawing this force versus time diagram. In this problem, we're told that there's a force that is being applied, and the rate at which the force is increasing is a constant rate, and that is why you see a straight line in this force versus time diagram. So it looks like the force starts out at 0 and it ramps up to 9,000 newtons, and it does so over a time span of 6 seconds, and then it drops off. So that is represented by this straight line, and it's going from 0 to 9,000 over 6 seconds. When you have a straight line, you can think of an average force. So I'll put AVG for the average force. You can think of this average force is equal to the force when t equals 6 plus the force when t equals 0 divided by 2, which would be 9,000 newtons plus 0 newtons divided by 2. So you can think of this average force is 4,500 newtons. If you think about the 3-second mark, all of the times prior to 3 seconds, the force is less than 4,500 newtons. And all the times greater than 3 seconds, the force is greater than 4,500 newtons. And since the rate of the force doesn't change, as evidenced by the straight line in the force time diagram, on average, you're going to have 4,500 newtons of force. So this force is ultimately being applied to a car that has a certain mass. But before we get into the specific parts of this problem, I also want to go over how impulse is related to force, how force is related to momentum, and therefore how impulse is related to momentum. So more specifically, we often use J as the symbol for impulse. You might have thinking that I would be the prime candidate. We often use a capital I for a concept which is intensity. So we're going to use J for impulse. And so then defining J generally, we say that it is the time integral of some force dt. And I'm going to make a case that we can say that that time integral of force dt can also be expressed as some change in momentum. So let's unpack this a little bit more. We know that force by Newton's second law is equal to mass times acceleration. We know from kinematics that we can express acceleration as the time rate of change of velocity. That's dv dt. So I hope you can see there that I'm just rewriting acceleration as the time rate of change of velocity. Momentum is defined as mass times velocity, not to be confused with mass times acceleration. Now, let's say that I want to take the time rate of change of momentum, which is to say that I would go dp dt. Mass is a constant, so that would come out and it would be m dv dt. this right here is exactly the same as this. And this right here is a way in which you rewrite force. And so this right here is equal to force. So in other words, force is equal to dp dt. Force can be expressed as the time rate of change of momentum. So consider this term right here. Force is the time rate of change of momentum. If I take that term and I plug it in right here for force, I get dp dt dt. Those dt's cancel. That just gives me the integral of dp. And so that's just going to give me some change in momentum. That's where it comes from. The key here is realizing that force can be rewritten as the time rate of change of momentum. And so that if impulse is defined as the force integrated over some time, then I can rewrite it to talk about how it equals the change in momentum. So these are key moves for being able to solve this problem. This problem has got 4 parts to it. The first part of it I actually already solved. It just wants us to solve for what is the average force acting over the 6 seconds. And so, as I pointed out, I evaluated the force at t equals 6 seconds, I evaluated the force at t equals 0 seconds, and then I divided by 2 to get the average. And so 4,500 newtons is our answer for part A. For part B, we are asked, what impulse does the force provide? So the impulse the force provides is going to be this average force that we just answered in part A multiplied by the change in time. That's equal to J. Another way you can think about this is if you have a force versus time plot, when you have a plot of something on your y-axis versus something on your x-axis, it turns out that the area under the curve is the integral over the entire time of interest. Let me show this to you. So you can imagine if you have force on your y-axis and time on your x-axis. Let's say that I drew a little mini rectangle like this, where the width would be dt and the height, if you can imagine, this is a very, very negligible width dt. So you can imagine that there's going to be some value of force, and that's essentially the height of the rectangle, and the width of the rectangle is dt. And that's where, you see you have an integral f. So that would be how high the rectangle is, and then dt is going to be the width of that rectangle. So when you do calculus, that dt is a limit as dt goes to 0. So of infinitesimally small width, as that dt goes to 0, then the height is precisely whatever the f is at that particular location. So if you can imagine then having a bunch of these tiny little rectangles, right? Start with the one on the far left, and then you have one next to that on the right, next to that on the right, next to the right. So just think of like a bunch of tiny little rectangles, but they add up. And each time, right, the height of the rectangle is the height of what the function is at that particular time. So that's essentially what like this right here, this is just Latin for sum. And so what you're doing is you're just summing up all of these tiny rectangles where each rectangle has a height of what the function is at that time and the width of what is that infinitesimally small dt. And so you add all of those green tiny rectangles up, and what you have is you have the area underneath your curve. So one way in which you could do this problem is you could just look at this and say it's a triangle, and this triangle has an area of 1/2 the base times the height. So one way you can think of it is you can think of this blue leg of the triangle as the base, and we know that halfway, which is about right here, the force is 4,500 newtons. That's what the average force was. So you have 1/2 your base, and then if you consider that right leg the base, the height of the triangle is just going to be this time duration from 0 to 6 seconds. So one way in which you can think of this is 1/2 base times height. Well, that's just equal to 1/2 F max times delta t, because delta t is 0 to 6 seconds. And remember, 1/2 F max, we had the average. You see how we divided by 2 here? This is just equal to the average force multiplied by delta t. So this would just be 4,500 newtons multiplied by 6 seconds. And that's why we can say impulse J for a force in which the force is increasing or decreasing at a constant rate, we can think of it as just simply the multiplication of the average force multiplied by delta t. And I showed you, if you think of that force versus time curve in terms of calculus, you're thinking of the area under the curve. And then if you think of it as the area under the curve, you can think of the base of the triangle as going from 0 force to 9,000 newtons force. So half of the base is 4,500 newtons. That's what I have written right here. And then the height, if you consider the up and down from 0 to 9,000 newtons is the base, the height is going to be from 0 to 6 seconds. So a little calculus in there. Sometimes those squiggly integral lines can look intimidating. Every time you see one of those, know that you're actually still just doing addition. What you're adding is you're adding a bunch of tiny little rectangles under a curve where the height of the rectangle is the distance from the x-axis to whatever the value of the function is at that particular point, and the width is an infinitesimally small bit of the x-axis. And so then if you just keep adding all those little rectangles, you get the entire area under the curve. So if you have a graph of something on the y-axis versus something on the x-axis, and there's a curve you draw out, the integral of the something on the y-axis multiplied by d, whatever it is on the x-axis. If it was t, it would be dt. If it was x, it would be dx. You're just simply summing all these tiny little rectangles to get the area under the curve. Part C of this problem says, let's say that the force that was ramping up from 0 to 9,000 newtons, what if this force was acting on a car that has a mass of 1,000 kilograms? M equals 1,000 kilograms. What is the change in momentum of this car? Well, it turns out, based on what we learned so far, we actually don't even need to plug the specific mass in yet, because I already showed, namely right here, that our impulse J can be thought of as the change in momentum. And again, that's based upon the work that I did here, where I showed you, starting with Newton's second law, how you could rewrite that in terms of the time rate of change in momentum. And then I plugged this new way of writing force, I plugged it in right here into the relationship between impulse and force and showed you how that becomes the change in momentum. So the impulse that we are solving for in part B, right here, that's just 4,500 newtons by 6 seconds. That's the answer to part B, and it's also the answer to part C, because the impulse is the change in momentum for the reasons that I've already shared. So your answer in part B should be the same as your answer in part C. And finally, in part D, they're like, okay, so imagine after 6 seconds when this force suddenly dies off, what's the car's speed going to be? You can probably imagine that if a force is being applied to the car for 6 seconds, it continues to accelerate the car for 6 seconds. It accelerates the car at an average of 4,500 newtons, but it's actually at the very end at 6 seconds when the force is at maximum. So this acceleration is continuing for 6 seconds. So you can imagine that the car's speed is going to be the most when the force finally stops. It's going to keep accelerating until it stops. So it's definitely at 6 seconds where the car is going to have the maximum speed, because it continues to accelerate and therefore the velocity continues to change over time. The slope of force versus time is positive, so that means that if you think of force versus time, then the slope, delta F, delta T, that's the acceleration. And so if the slope is positive, the acceleration is positive. So if acceleration is positive, the velocity keeps increasing. So you better bet that from 0 to 6 seconds, if you have a force that is being applied at a constant increase, then the acceleration is going to remain positive and it is going to keep increasing that velocity all the way to where it dies off at 6 seconds. So therefore I know that it's going to be right here. This is going to be when the car has its maximum speed based on this applied force. But we need to figure out now, well, what is that? So we can simply take the fact that we now know the mass of the car. We know that impulse is equal to the change of momentum, as shown before. Well, that is equal to the change in mass times velocity. Mass remains constant, so I can bring the mass out and I can say mass times the change in velocity. So if impulse equals the mass times the change in velocity, then if I divide by m, I can say that the change in velocity is equal to the impulse divided by m. We know what the impulse is. It's been the answer for parts B and C. It's just this 4,500 newtons times 6 seconds. And so that's going to go right here. And then right here, that's our mass equals 1,000 kilograms. That's the mass of the car. So just to review, impulse is thought of as a force being applied to an object over an amount of time. From a calculus perspective, we can think of it as the time integral of force dt, where we would integrate from some time initial to some time final. I made a case that you could equate that with the change in momentum over the same time interval. That's because force can be expressed in terms of the time rate of change in momentum. Once we know what an impulse is, we can determine how the velocity changes because we know that the impulse is related to the change in momentum. In a problem where a force is applied over time and the rate in which that force increases or decreases is constant, which is to say the slope of force versus time is a straight line, we can think of the force as an average force being applied over that time interval, where we simply take the force at the end of the time interval plus the force at the beginning of the time interval divided by 2. I showed you how with a plot of force versus time, you can also think of a curve where the area of the curve is the integral over that time period. And I showed you how, thinking of this as the area under the curve, you could also think of the curve as a triangle where the area of the triangle is 1/2 base times the height. And I tried to relate the base to the y-axis, which was the force, and the height, which was the x-axis, or in this case t-axis, which was the time. So just one more time. Impulse is J, okay? Impulse is not I. Impulse is J. It's the integral of a force over time, but you can express this as the change in momentum of an object as well, because you can express force in terms of momentum. More specifically, force is mass times acceleration, but acceleration is the time rate of change of velocity. And so if momentum is mass times velocity, then mass times the time rate of change of velocity is the change in momentum. So force can be expressed as the time rate of change in momentum. And so then if we substitute F equals dp dt into the J equals the integral of F dt, that means that J equals the integral of dp dt, which is just dp, which is to say that momentum, or should I say impulse, is just the integral of dp. Well, the integral of dp is just going to be the change in p from some final point to some initial point. Impulse very much can be helpful in thinking of how velocity changes over a time interval, because impulse over a time interval is precisely the change in momentum. And assuming the mass of the object doesn't change over that time interval, then it's going to be the velocity change of that time interval that manifests in the momentum change of the time interval, which again can be thought of as the impulse over that time interval. So that's how you're going to solve problem number 2 on problem set number 5. A quick addendum to number 2. I explained the symbolic calculus in terms of a graphical representation. And I also think I should work out the mathematical symbolism as well to convince you that you can think of the impulse in problem 2 as the average force multiplied by the amount of time that elapsed. So let's go back to this idea that impulse J, and again, not to be confused with intensity I, can be expressed as an integral where you have f dt. And in this particular problem, we are going to do a definite integral where we are going to go from time equals 0 to time equals 6. And again, this is an addendum of the problem that I worked out, where I showed you a graphical depiction of force versus time. So going from 0 to 6 is like going along this horizontal axis, where you can imagine that you have a bunch of these green rectangles. The width of each of those green rectangles is dt. That's what you see right here. And the height of each of those rectangles is going to be what the force is at various points along this graphical depiction of force. That's what you have right here. I talked about how you could think of that graphical representation as a triangle and think of the area under the curve and think of 1/2 base times the height, but I'm going to also, to be complete here, work this out symbolically. When you have force versus time and the slope of force versus time, which happens to be the change in force over the change in time, when you have a straight line, that means that the change in force over time is going to be the same at all points that are depicted. because that was the case, we could think of, and I'll go back to my example, if you went right in the middle, that's when the force was 4,500 newtons. All of the points to time being greater than 3 seconds are going to have forces that are greater than 4,500 newtons. All of the time points before 3 seconds, force is going to be less than 4,500 newtons. But because the relationship between force and time is a straight line, we can say that there's an average force being applied, which is the sum of the force at 6 seconds plus the force at 0 seconds divided by 2. We can't do that if the force was some function of time that wasn't a straight line. Like imagine that the force looked something like that. Then we can't just say that it's the average force multiplied by the time duration. But we do, in this particular problem, have the luxury of going to the integral and saying that we can treat the average force as a constant that goes outside of the integral, such that we can now integrate dt from 0 to 6. So again, because it's a straight line in blue and not a red squiggly line in red, that's what gives us the ability to treat the average force as a constant in this integral. So now continuing with our integral, f average again is a constant, and now when we integrate dt, that's simply going to be equal to time, and we are going to evaluate that time from t equals 0 to t equals 6. This is a definite integral. If this was an indefinite integral, the integration of dt would be t plus some constant c. But the thing is since it's a constant c, with a definite integral, you evaluate the integral at both a final point and initial point. So for instance, you can imagine if it was t plus c evaluated at t equals 6, and then t plus c evaluated again at t equals 0, when you subtract the evaluation at t equals 6 from the evaluation at t equals 0, the constant's the same in both of those terms, and so the constant washes out. So you don't have to worry about constants when you're talking about definite integrals. So this simply is going to be f average multiplied by t equals 6 minus t equals 0. And that quite simply is going to be f average multiplied by 6 seconds, which again, this is equal to f average delta t, which, as I showed you symbolically, you could think of as the area under the curve of force versus time. But I also wanted to show you how you can solve this symbolically. And just to close the loop here, you could think of this term right here, f average, as 1/2 of the base of our triangle, where this right here, this blue line right here, that's the base. So 1/2 of the base, 4,500 newtons. And you can think of this delta t term right here as the height, where in black right here, that would be the height from t equals 0 to t equals 6. So this is how symbolically you can also think of the impulse in this problem as equal to the average force multiplied by the time duration, which in this case is 4,500 newtons multiplied by 6 seconds. So that's an addendum to problem number 2 from problem set number 5. This is problem number 5 from problem set 5. There will be an exam problem just like this one on the upcoming exam. In this problem, we've got two masses of two different blocks. In the problem, it says that there's a bullet of mass little m. I'm going to be even more specific, and I'm going to call it mass little m1. And it's fired into a block of big M mass, which I'm going to be more specific and call capital M2. And the idea is that you're going to have, at one point,
a bullet and a mass, and then at some later time, you're going to have the bullet embed itself into the mass. So you can imagine you can treat this problem like a collision problem, where this would be a perfectly inelastic collision, which is to say that before the bullet hits the mass, we can say the mass of the bullet, which is little m1, and whatever its initial velocity is, which I'll call v1 naught, plus the mass of the bigger block, capital M2, and whatever its initial velocity is, so v2 naught. That's at this time right here. And at some later time, when the bullet embeds itself in the block, we can now think of a combined mass moving at some combined velocity. So continuing with this perfectly inelastic collision, I can say the combined mass of the bullet plus the mass of the block, and I'm going to call this VC for combined, which is the combination of the mass of the bullet and the block, and I'm going to call it VC initial. The reason I'm calling it VC initial is because we have another step to this problem where now the combined mass is going to slide and it's going to encounter friction and it's eventually going to come to a stop. And this problem wants us to figure out, given a certain coefficient of kinetic friction, if it takes a certain distance to stop, then what must the velocity of the bullet originally have been? So this problem involves knowing a perfectly inelastic collision and how to set it up. That's what I just did. But it also involves us understanding the idea of the work energy theorem. And so more specifically, if I think of the net work, so W for work, and I want to think of the net work that's done on a problem where a bullet embeds into a block and then encounters friction as it slides to a stop, then I have to think of my net work as a combination of the work done by conservative forces, which I'll call WC, plus work done by non-conservative forces, which I'll call NC. So there are videos and other resources to help you with the idea of a conservative force. This is a problem where the focus is not so much on talking about what differentiates conservative forces for non-conservative forces, but what I will say is that a conservative force is a force where if negative work is being done by a conservative force, that work, which is negative work, can be stored as this concept that we call potential energy that could be turned back into kinetic energy at some later time. So an example would be gravity. Gravity acts down. If I lift an object upward and move it upward, that means gravity is doing negative work because the force of gravity is down and the displacement is up. When we do this, we say that there's an increase in gravitational potential energy. If we let go of the object, gravity now starts doing work positively because gravity still is down, but now the displacement is down. And what's happening is that this potential energy that was stored up by gravity doing negative work is now being transitioned into kinetic energy by gravity now being able to do positive work. Another example of a conservative force is a spring. If you can imagine a spring at its rest length and you press it to squish the spring, then what's happening is that if you can imagine your hand squishing on a spring, your hand would feel a force opposite the direction the hand is moving, and that's because the spring actually, and we call this Hooke's law, is pushing back. And it's pushing back at a rate that is proportional to the spring constant and how much distance you're making the spring squish from its equilibrium. Similarly, if you took a spring from its equilibrium and you stretched it past its equilibrium, the force now would be in the opposite direction. And again, what's happening here is that when a spring, just like gravity, is doing negative work, which is to say when the force of the spring is opposite the direction of the displacement of the spring, potential energy is storing up. And then if you let go, the spring gets its way and it wants to go back to equilibrium, and it exerts a force that's in the direction of motion, which means it's doing positive work, which means it's now accelerating the object and it's gaining kinetic energy. So both in the case of gravity and in the case of the spring, if negative work is being done, we can get that work back later. That's what it means to be a conservative force. In this problem, after the bullet embeds itself in the larger block, it slides and encounters friction. Friction is a non-conservative force. What happens is that if you can imagine, the friction is going to create thermal energy, it's going to create sound energy, and we can't get that back later like we can with gravitational potential energy or elastic potential energy. In this problem, if you can imagine a free body diagram, so if I represent after the bullet gets embedded into the block, so you can imagine this is little m1 plus m2 g. That's the force of gravity acting down on the combined bullet block. Now, if it's on a table, the table pushes back. That's our normal force. And in this problem, since we've got some bullet going at some initial velocity, and that's what the v1 naught is, if the mass that's sitting there before the block hits it is stationary, then v2 naught equals 0. And once the bullet embeds itself, you can imagine that there is some v combined 0 going to the right, which is to say that the combination of the bullet and the larger mass is moving to the right. If it's moving to the right, that means that there is some friction to the left, because the kinetic friction always opposes the direction of the motion. And so I can say that the kinetic friction is going to be equal to whatever the coefficient of kinetic friction is multiplied by the normal force. Since I have a free body diagram in both the horizontal and vertical direction, I can sum the forces in the y direction, and that will be the normal force. If we're going with our conventional coordinate system, where you have plus x to the right and plus y going up, then the normal force will be positive, and then the gravitational force, which is m1 plus m2g, that will be negative. And then in the y direction, which equals 0, because there is no acceleration in the y direction. This problem is just about horizontal motion. And that means that I can say that the normal force is equal to m1 plus m2g. And that's helpful for me because this term right here goes right there. Remember, kinetic friction is the product of both the coefficient, which tells you about the nature of the interface. Is it rough or is it smooth? But then it's another thing to tell you how much the surface is pressed up against another surface. That's the normal force. So we've got a problem here where friction is definitely going to be doing work, and it's going to be doing negative work because the motion is to the right and the friction force is to the left. And even more specifically, it's anti-parallel. So if we think about the angle between the displacement and the kinetic friction force, the angle is 180 degrees. The cosine of 180 degrees is -1. Now, there is gravity in this problem, but see in the free body diagram how gravity is acting straight down and the displacement is horizontal. So if you have a force that's perpendicular to the direction of displacement, then the cosine term in the work equation is going to vanish. For instance, the cosine of 90 is 0, okay? The cosine of 270 is 0. Let me be a little bit more specific. I can describe this net external work as an integral f dot dx, where this problem we're talking about just motion in the x direction. So that's why I'm going to say dot dx. And with a dot product, I can rewrite this as the integral of the magnitude of the force. And again, this is the net force. And I'll unpack this more in a second. The magnitude dx cosine theta. This is why I was mentioning cosine theta a second ago. If cosine theta, for instance, is 0, that means that the force and the displacement are parallel. Cosine 0 is 1. If the force and the displacement are perpendicular, cosine theta would be, say, cosine 90 or cosine 270, and that's 0, and so you have no work. And my point here is that when you talk about the gravitational force, and I just underlined it in the free body diagram, acting downward, if the displacement is completely horizontal, this cosine theta term vanishes, which is to say that yes, there is gravity in this problem, but gravity doesn't do any work in this problem. And you could say the same thing about the normal force. The normal force exists, sure, but it's completely perpendicular to displacement. So what happens here is that this is a problem where we don't have any work being done by conservative forces, and what we're left with is the work done by non-conservative forces. And so, quite simply, this is the work that's done by kinetic friction, which I'll say W with the index Fk. So we need to figure out how much work is done by the kinetic friction, and by the work energy theorem, we can say that the net work that is done on our system is equal to the change in kinetic energy of our system. And the change in kinetic energy in our system, as I will unpack later, is going to be 1/2 the mass of our system, V final squared, minus 1/2 the mass of our system, V initial squared. Now again, when I say final initial now, I'm talking about initial is when the bullet embeds itself into the larger block. That's the initial velocity. That's this V combined initial. And then it's going to slide and it's going to come to rest. And so the final velocity of our system after the friction does negative work is going to be 0. But I just want to stop and say that the work net can be thought of as the work of conservative forces and the work of non-conservative forces. In this problem, the conservative force, gravity, does no work because it's perpendicular to displacement. So we're left with only non-conservative forces, which in this case happens to be the work done by kinetic friction. And again, a non-conservative force is a force where if it does negative work, we can't get that work back later. Gravity, if we do negative work, we can get it back later because gravitational potential energy can transition back into kinetic energy if gravity is allowed to do work in the direction of displacement. Same thing with a spring. But with friction, it's lost due to sound, due to thermal dissipation. We don't get it back. So we need to figure out now how are we going to express this work done by friction and then equate it to the change in kinetic energy, both right when the bullet embeds itself and then when the bullet block combo comes to a stop. The friction, as I showed in the free body diagram, that's this term right here, is going to be equal to the coefficient of kinetic friction multiplied by the normal force. And the change in kinetic energy, as I mentioned, is going to be equal to 1/2 the combined mass of the bullet plus the block, whatever the velocity of the combined mass is, squared. And again, this is when it comes to a stop. So I can tell you already that we've got a simplification because that term is 0. And when you're talking about change, you're talking about final minus initial. So the initial, when the bullet embeds itself into the block, is M1 plus M2 V combined initial squared. That's this term right here. That's just as the bullet embeds itself into the block. Now remember, this is equal to this term right here. So I'm going to express this term out more specifically now, where I know that the force is going to be this force of kinetic friction. So more specifically, I can say that the integral of the magnitude of the force is going to be the coefficient of kinetic friction, the normal force, dx. And remember, the friction is going due left because the motion is going due right. And so the cosine is 180 degrees. That term is -1. So what I can do is I can bring out my constant terms and that -1. And more specifically, I already showed that the normal force can be expressed as the combined mass multiplied by g. And again, we have our coefficient, that's a constant. Cosine 180 is -1. So I can have a -1. I can have mu k, that's a constant that comes out. And remember, the normal force is the combined mass multiplied by g. And after I do all of that, now in my integral, I just have a dx. That's going to be an easy integral to pull off. And dx is going to go from x equals 0 to x equals d. So d is going to be the total distance that this combined bullet block combination slides before it comes to a stop. If you can imagine, the integral dx is just x, and I would evaluate it from x equals d to x equals 0. So this is just going to be minus mu k, right? I just have the -1, mu k, mass of the bullet, mass of the block, g, and then d. And again, that d comes from, if I integrate dx, I'm just going to get x plus some constant evaluated at d minus x plus some constant evaluated at 0. The constant's the same in both cases, so when you subtract one from the other, the constant washes out. So you don't have to worry about constants when you're talking about definite integrals. So d plus c minus 0 plus c is just d, and that's what this d is right here. So now I have this expression for the work that has been done by the coefficient of kinetic friction multiplied by the normal force, which is to say the kinetic friction force, which is opposite the direction of motion. That's what all of this is right here. That is the work done by the kinetic friction. And it shouldn't be surprising it has a negative sign because it's opposite the direction of displacement. And all of that, remember, is equal to all of this. That's the change in kinetic energy. This is the work energy theorem. That's this right here. The net work is the work done by conservative forces plus the work done by non-conservative forces. By my earlier reasoning, there is no work done by conservative forces. In this case, gravity is a conservative force, but gravity is acting perpendicular to the motion. So there's only work done by non-conservative forces, which in this case is the work done to kinetic friction. So at this point, it's just algebra, because what this problem wants us to do in part A is it wants us to find an expression for the bullet speed. And that is that term right there. That's V1 initial. That's the speed of the bullet. when it's fired and before it lodges itself into the block. So what I can do, you see the two, and I'll just do it again for emphasis. So you have this term right here equated to this term right here. Remember, one of the terms already drops out because we know that the final velocity of the bullet block combo is 0. So I'm going to pick a different color here for contrast. I'm going to go ahead and pick orange. And what I'm going to do, and again, this is work energy theorem, I'm going to say that negative 1/2 mass of the bullet, mass of the block, the combined velocity initial, this is right when the bullet lodges itself into the block, is going to be equal to minus mu k, that's the coefficient of kinetic friction, mass of the bullet, mass of the block, g d, where d is the distance it slides before it comes to a stop. This term right here, the velocity combined initial, that's this term right here. And as you see, we can relate that to what the initial bullet velocity is. More specifically, before the bullet lodges itself in the larger block, the block is at rest. That's what this 0 term right here is, which is to say this term is 0. And so if that term is 0, so I'm also going to change color for contrast again. I can say that we have an expression, the velocity combined initial can be written in terms of the velocity of the bullet initially. And that's what we ultimately are asked to write an expression for. So by that equation, I can say that mass 1, which is the bullet, V1 initial, is equal to the combined mass of the bullet block combo, and then whatever the initial velocity is, that combination. That's all from this equation right here. This is a perfectly inelastic collision. So now what I can do is I can express the combined initial velocity in terms of the initial bullet velocity. And to do that, I simply divide both sides by the quantity m1 plus n2. So V combined initial is equal to mass of the bullet's initial velocity divided by the quantity m1 plus m2. This term right here can go right in there. And when you do so, you can see that now you have an expression where you have a V1 naught, that's this term right here, and that's what you want to solve for with this expression in part A. You want to write an expression for V1 naught. I can simplify a little bit more in the orange because I have the combined term here and I have the combined term here. I also have a negative sign on both sides, so I can get rid of that. So what I can say now is the V combined initial squared is equal, if I multiply both sides by 2, because I have a 1/2, you see right here, if I divide both sides by 2, then what I'm going to get is a 2 mu k, and I'm going to have a g for gravity and a d for the total displacement. That came from my integral. And if I want to then express for V combined initial, I can substitute this right here. When I do that, I'll change another color here because we got a lot of numbers and symbols here. So to provide some contrast, what I can say is M1 V1 initial divided by the quantity mass of the bullet plus mass of the block squared. Again, what I did is I just took this expression right here. You see VC naught? And you see how this is VC naught? So I just substituted it. So now you have all of this squared. That's what you see in the bracket squared there. That is equal to M1 squared V1 naught squared divided by little m1 plus m2 squared. And all of that is still equal to 2 mu k g d. Now what I can do you see how I have this V1 naught squared term? I can do some algebra where I can isolate that all on one side, and then I will be able to take a square root and I'll have an expression. So forgive me, but we're going to have to go to a fresh page because we've run out of real estate here. But I just want to let you know before we move to the next page, I want to write an expression that isolates for this V1 naught squared. Because this V1 naught squared, that is the initial bullet velocity, and that's what we want to write an expression for. So what I'm going to do on the next page is I'm going to divide both sides by this m1 squared term, and I'm going to multiply both sides by this m1 plus m2 squared term. That will isolate this term right here. So to the next page we go. This, remember, is problem number 5 in problem set number 5. So this is the continuation. So what I'm going to do, again, is I'm going to isolate this V1 naught squared term because I want to write an expression for V1 naught at the end of the day. So to do that, V1 naught squared is equal to 2 times m1 plus m2 squared mu k gd divided by m1 squared. And again, the reason I got that is because I wanted to isolate for this term right here, so I divided both sides by m1 squared. So you see how there's an m1 squared in the denominator here now? And then I multiplied both sides by the quantity m1 plus m2 squared, and that's why you have this term in the numerator now. Now again, I want to solve not for the expression of the bullet's initial velocity squared, but the bullet's initial velocity. So what I do now is I take the square root of both sides. And when I take the square root of both sides, I get the following expression. V1 naught, that's the velocity of the bullet initially, is equal to the square root of 2 mass of the bullet plus mass of the block squared mu k g d, and that is divided by m1 squared. That's the mass of the bullet. I can simplify this more specifically. I have an m1 plus m2 squared underneath the radical, which means I can bring it out. I can say m1 plus m2. I have an m1 squared in the denominator. That's under the radical. And so I can bring that outside the radical as just m1. And then what's left inside of the radical, which is inside of a radical, is sometimes called the discriminant. The discriminant is 2 mu k g d. This is an expression, v1 naught. This is an expression for the initial velocity of the bullet. So going all the way back here, okay? When the bullet is fired prior to hitting the block, it has some initial velocity. When we, using the work energy theorem, knew that friction is going to be doing negative work to eventually bring the bullet block combo to a stop, we now have an expression that tells us what the initial velocity of the bullet must have been for the bullet block combo to do a distance d before it comes to a stop. That is the expression. And so then, remember, this is part A to get the expression. For part B, we're then given a bunch of values, and quite simply, we just need to plug them into our expression. So more specifically, we're told that the mass of the bullet is equal to 8.0 grams. We want to convert that to kilograms because that's the standard SI unit. And so there are 1,000 grams in 1 kilogram. So we simply take 8 and divide it by 1,000, which is another way of saying that we take the decimal point and we have it go 3 steps to the left. So not 0.8, not 0.08, but 0.008. So this would be equal to 0.008 kilograms. We are told that the mass of the block is equal to 12 kilograms, and that's already in our SI unit, so that's nice. We are told that the distance that the bullet block combo slides before it comes to the stop is equal to 6.0 centimeters. So we got to convert this as well. So to convert this, I know that if you've got 100 centimeters, you have 1 meter. And so in this case, I need to take that 6.0 and I need to take that decimal point not to 0.6, but to 0.06. I have to have it slide 2 spots to the left. So that's equal to 0.06 meters. Notice in both of the conversions I did, right? I have a gram I start with, and I want to get to kilograms, so that means that I'm going to need to find a conversion where I also have a gram in the denominator. Each of the columns is an equality, and you multiply the columns together. Same here. See how I get centimeters cancel out, and I'm left with meters. But I multiply. In the first case, I multiply 8 times 1 divided by 1,000. In the second case, I multiply 6 times 1 divided by 100. Finally, I am told that the coefficient of kinetic friction is equal to 0.20. So this is going to be enough to solve, because check this out. Mu k. That goes right there. All right. D. That goes right here. M1, that goes right there, and also right there. And finally, M2, that goes right there. So you use the expression for V1 naught, which again is the velocity of the bullet at the beginning. That's part A. You have to write the expression. And then in part B, you take the values you're given, you make the necessary conversions into SI units, and you essentially plug and chug into the expression that you found in part A. So to review, lots of physics going on in this problem. We have a perfectly inelastic collision. After this perfectly inelastic collision, we then have work being done by the non-conservative force of friction. We talked about the work energy theorem. The work energy theorem tells us that the net work on a system is going to be equal to the conservative forces plus the non-conservative forces. The work due to the conservative forces, the work due to the non-conservative forces. Together, that equals the change in kinetic energy of the system. I explained what conservative forces were. The only conservative force there was a possibility in this problem was gravity, but because gravity was perpendicular to displacement, there's no work done by gravity, so we're left with non-conservative forces like friction. Then I showed how you can use the integral for work where we substitute the expression for the force of kinetic friction. At that point, it's algebra. And we ultimately symbolically manipulate our algebra so that we can isolate for V1 naught. V1 naught is the velocity of the bullet at the beginning before it engages in a perfectly inelastic collision when it lodges itself into the block. We wrote an expression for this velocity in terms of the masses, in terms of the coefficient of kinetic friction, in terms of gravity's acceleration, and in terms of the distance that the block bullet combo travels before it comes to a stop. And then in part B, we're given our parameters, and it's essentially plug and chug into the expression we symbolically manipulated in part A. So that concludes question number 5 from problem set number 5. This is problem number 9 on problem set 5. There will be a problem exactly like this on the upcoming exam. In this problem, we have a coin. We are told the mass of the coin is equal to 5.5 grams. Let's go ahead and convert that to SI. If I want to get rid of grams, I'm going to have grams downstairs. I want to eventually convert to kilograms. So the conversion for 1 kilogram is 1,000 grams. So you see how the grams cancel. You multiply adjacent columns. So this would be 5.5 multiplied by 1 over 1,000. Since you're dividing by 1,000, you need to take the decimal place and move it 3 spots to the left. So not to 0.5, not to 0.05, but to 0.005. So this equals 0.005 kilograms. All right. We are told that this coin is thrown from a height. So if we're going to be talking about height, let's get our coordinate system on the board here. Let's do the conventional to the horizontal right is positive x, to the vertical up is positive y, which is to say to the horizontal left is negative x, and to the vertical down is negative y. So we are told that y initial, so this is at the bridge height. Y initial is equal to 25 meters. And we are going to let the surface of the water below, which we will call y final, let's set that equal to 0 meters. which is another way of saying that the height is 25 minus 0. H equals 25 meters. For part A, we want to determine the work done by gravity. And more specifically, this coin is going to go from a bridge that is 25 meters above the water down to the water. It's going to be going down, which is to say it's going in the negative y direction. We know near the surface of the Earth that gravity is proportional to an object's mass times the acceleration due to gravity near the surface of the Earth, which is 9.8 meters per second squared. And that it is always down. The acceleration due to the gravitational attraction towards the Earth is towards the center of the Earth. It's down. So we're going to have a situation where the object's going down and the force of gravity is also acting down. So this is going to be a situation where positive work is being done by gravity. So I'm going to work out in part A what the work being done by gravity is, and then I'm going to relate that to the work energy theorem in part B, because in part B, they're going to ask us for what the speed of the coin is just as it hits the water. And so if we know what the work done by gravity is, we could use the work energy theorem to figure out kinetic energy. And kinetic energy involves velocity, and that allows us to solve for part B. But first things first, we need to figure out the work being done by gravity to accelerate the coin from a height of 25 meters, that's the height of the bridge, down to the surface of the water, which we are calling 0 meters. So the total height is 25 meters. The work done by gravity can be equated to an integral where we've got some force, and in this case the force is going to be the force of gravity, and more specifically it's just the force of gravity acting downward in the y direction. So I'm going to say a dot product with a position vector y, which is in the vertical direction. So I'm figuring out the work done vertically because I know this problem is a problem that is just pertaining to the vertical direction. This is a dot product. And another way of expressing a dot product is to think of the magnitude of the first vector, the magnitude of the second vector, and the cosine of the angle between the two vectors. These are definite integrals, so we also have to specify our beginning and ending points. These are integrals that are set up in the vertical direction, which is to say the definite integral is going to span from y initial to y final. Well, we know that y initial is 25. We know that y final is 0. So I've specified the limits of my definite integral, but I still have a little bit more work to do because I need to think about this theta. What is the angle between the force of gravity, which is negative mg, negative because it's going straight down, and I've defined straight up as positive y. And what's the displacement? This force right here, I'm going to resubstitute as negative mg. This is just dy, which is just the magnitude, or you can call it the scalar of dy, which is the differential displacement vector in the vertical direction. And I still got this cosine theta term. So if the force of gravity is acting straight down and the coin is going straight down, then this theta term right here is equal 0, which is to say the force of gravity down is parallel to the displacement down. The cosine of 0 goes to unity. This simplifies my integral such that from 25 equals y to 0 equals y, I have negative mg dy. Remember, the cosine term went to unity. I can further simplify. I can take the constants outside the integral. So I can say negative mg dy from 25 to 0. The integral of dy is just going to be y plus a constant. And with a definite integral where we evaluate at the final initial positions, the constant's the same in both, and so it washes out, which is to say this is equal to minus mg y, and that's evaluated from 0 at the final position and 25 at the initial position. This is equal to minus mg times 0 minus 25. See how you have a negative sign here and a negative sign here. And so the final is going to be 25 mg. Another way of expressing this is mgh, where h is 25, as I expressed up here. Those of you that are learning about the work energy theorem, and more specifically about potential energy, and even more specifically about potential energy due to gravity, this mgh might look familiar to you, because that is what we describe as the gravitational potential energy. It's mg and some height above some reference point. We'll get to more of that a little bit later on. But the point here is that for part A, we have now calculated what the work done by gravity is. And the work done by gravity, going from a bridge of the height 25 meters down to the surface of the water, is actually a positive value. It's 25 mg. That's because gravity's doing positive work. And I say it's doing positive work because the direction of the gravitational force is straight down and the coin is going straight down. So that means that the force is in the same direction as the displacement. That's positive work. And even more specifically, it's parallel. And that's why you had cosine theta equals 0, and therefore cosine of 0 going to unity. So that is part A. Part B, now we know that the work done gravity, we can actually solve for what the velocity of the coin is just as it hits the water, and we can do this with the work energy theorem. And more specifically, the work energy theorem states that the net work done on a system is going to be equal the work done by conservative forces and the work done by non-conservative forces. In this problem, there are no non-conservative forces. In fact, there's only one force that we need to worry about in this problem, and that's the force of gravity. Force of gravity is a conservative force because when gravity does negative work, potential energy stores up, which we can get back in the form of kinetic energy. And so think about if we played this problem in reverse. Let's say we had a coin at the surface of the water and we lifted it up to the height of the bridge 25 meters above. In that particular scenario, we are lifting the coin straight up, even though gravity is acting straight down. That means that the displacement vector and the force vector of gravity are anti-parallel. That means that theta equals 180 degrees. The cosine of 180 degrees is -1. So do you see how when gravity is acting down and displacement is up, gravity is doing negative work? But here's the thing. As gravity does negative work, potential energy is storing up. And that potential energy we can get back in the form of kinetic energy if gravity is allowed to begin to act in the direction of displacement. And that's precisely what happens if you lift up from the water level to the bridge level, and you do so, say, with your hand, and then you let go. Gravity now starts acting down, displacement is down, work is positive now. So the potential energy that was stored up when gravity did negative work now gets paid back with gravity doing positive work. That is the essence of a conservative force. As explained in other videos, another example of a conservative force is a spring. Examples of non-conservative forces are friction forces. We certainly don't have friction forces in this problem. If we did, if we had air drag that we had to consider, then we would have to consider non-conservative forces. But in this particular case, we don't have to worry about this term. And so the only term that we need to worry about are our conservative forces. And it turns out we've already done a lot of this because in part A, we solve for the work done by gravity. And that's the only conservative force in our problem. So here's the key. Once we know what the sum of our conservative and non-conservative forces are, we know that's equal to the change in kinetic energy of the system. That is what the work energy theorem is. The work energy theorem is that W net, which is the sum of both conservative work and non-conservative work, is equal to the change in kinetic energy. And that change in kinetic energy is 1/2 mv final squared, which in this case would be the velocity just as the coin hits the water. That's what we want to solve for. And the initial kinetic energy is 1/2, same mass, then velocity initial squared. We're given what this initial velocity is. By the way, if we drop the coin, the initial velocity would be 0. But actually in this problem, there is a velocity applied right at the beginning. But that's no big deal. We can solve for that too. And I'm going to show you how to do so. Now remember, we already solved, and I'm going to circle it. We already solved for the work done by gravity. This is WG. So 25 mg. That's equal to all of this stuff right here. Let's change colors. 1/2 mv final squared minus 1/2 mv initial squared equals 25 mg. We can do some simplification. A mass is in each term. Also, I can get rid of the 1/2 by multiplying each term by 2. So I can have v final squared minus v initial squared is equal to 50g. I can isolate for v final, which I want to because that's what I want to solve for. V final squared, again, this is going to be the velocity of the coin just as it hits the water, just as it's fallen from 25 meters up down to what we're going to call 0 meters at the surface of the water. This is after gravity has done work on it over 25 meters. And positive work because downward is the same direction as the force of gravity, which is downward near the surface of the earth. So VF, which is V final squared, and again, this is of the coin, that's going to be equal to 50G plus V initial squared. In this problem, we are told that V initial is equal to 4.0 meters per second. I'm going to do one more step, and I'm going to leave you to plug in the numbers. But since I have a V final squared, I can square root both sides such that V final is equal to the square root of 50G plus V initial squared. G is 9.8. And this term right here, V naught, well, that term you can just put right there. Make sure you square it, of course. If you square it, 4.0 meters per second is going to be 16. So underneath the radical you see there, which is some kind of called discriminant, it's going to be 50G plus 16. So you go 50G plus 16, take the square root, and you should get 22 meters per second when you do that. The key here is that in part A, we solve for the work done by gravity. We get a positive value. That's this term right here. It should be positive because gravity acts down the displacement once you go from a bridge of 25 meters up down to the water. The displacement is straight down. The force of gravity is straight down. That means that the angle between the two is 0. The cosine of 0 is 1. So you have positive work being done by gravity. Positive work being done by gravity is the only work in this problem. There is no friction. We don't have any non-conservative forces. We have one and only one conservative force. That's the work done by gravity in the displacement direction of straight down. Now, the next thing is that we know that the net work on a system equals the change in kinetic energy of the system. That is the work energy theorem. We know kinetic energy is 1/2 mv squared. So that means the change in kinetic energy is the kinetic energy final minus kinetic energy initial. That's where you get this expression right here. Now that we have that expression in orange, I show you with algebra how you can isolate for V final. V final is the velocity of the coin just as it hits the water. And I show you how you can write that as an expression of both G, which is the acceleration due to gravity near the surface of the earth, which is 9.8 meters per second squared, and V naught, which in this problem happens to be 4.0 meters per second. If this was a problem where you just drop an object, V naught would be 0. You'd solve it the same way, it's just that V naught squared term would vanish. So this is a problem where if you ran it in reverse, I hope you can see how gravity doing negative work means that gravitational potential energy is adding up. In other words, if when it falls in the direction of gravity, gravity does 25 mg, which is the same thing as saying mgh. If gravity does mgh of positive work, when gravity's direction is parallel to the direction of displacement, when gravity's direction downward is anti-parallel to upward displacement, it's doing negative work in precisely the same amount. So if we ran this problem backwards, gravity would do negative mgh of work. That's not a coincidence to when we say gravitational potential energy is mgh. That means that when gravity does negative work, there's an mgh of gravitational potential energy that gets stored up. And when you think of the word potential, it means there's a potential that work can be put to positive work. So think of it as when gravity does negative work, potential energy stores up and it can be spent at a later time doing positive work. So precisely the negative work of lifting an object against gravity, a height h, if you were to let go, gravity would start having the object go in the same direction as gravity, and over the same distance would do precisely the amount of positive work as negative work was done to lift the object to height h against the direction of gravity. This problem very much underscores the work energy theorem. And one last time, the work energy theorem is thinking of the net work done on a system as a combination of the conservative work being done and the non-conservative work. Examples of conservative forces doing work are gravity and springs. Examples of non-conservative forces doing work are friction. This was a problem where there were no non-conservative forces. It was only one conservative force, i.e. the force of gravity. Once we knew it was just the force of gravity contributing to the net work on the system, by the work energy theorem, we could equate that to the change in kinetic energy of the system. Kinetic energy, of course, involves velocity, more specifically the square velocity. And so that was our ticket to eventually having an expression for V final, which is the velocity of the coin just as it hits the water. And as I said, regardless of what the initial velocity is, this is a general expression where you could just plug in what that initial velocity is, square it, and then in this particular case, you would add 50g and then take the square root. So that is how you solve problem number 9 in problem set number 5. This is problem 10 on problem set number 5. I'm going to show you how you can calculate the work done on a particle where instead of just being given a force that can be treated as a constant, the force can actually vary as a function of position. And so more specifically, imagine that we have a particle and that particle has a force that's acting on it, and we'll have that force in this problem act in the positive horizontal, or more specifically positive x direction. And that's by using the familiar coordinate system where to the right horizontally is positive x and upward vertically is positive y, which is to say that to the left horizontally would be negative x and downward vertically would be negative y. In this problem, we are given an expression for this force that is going in the horizontal direction. And more specifically, that expression, f with the index of x, so again, this is going in the horizontal direction, is equal to some coefficient q multiplied by the square of x. So you can see that as x gets larger and larger, which is to say that as the particle moves further and further to the right in the horizontal direction, the force in that horizontal direction is going to increase exponentially. So what we are going to do is calculate the work done on this particle by using this expression and using the calculus integration for work, which, if we use the letter W to stand for work, and we are interested in evaluating that work from some initial position of x equals 0 to some later position of x equals some distance d away from that 0 point, we can say that that is equal to a definite integral where we're integrating from 0 to d, and we are integrating the what's called dot product of the force and some differential element x. And so before I get any further, if I've got a dot product between two vectors, let's say I've got some vector A and I've got some vector b. There's two different ways you can think of this dot product. So the first way you can think of this dot product, A dot B, is to take the x component of A and multiply it by the x component of B. That's a scalar. And then you add the y component of A multiplied by the y component of B. So a dot product between two vectors is a scalar. And one way you can get that scalar is by taking the x components of the two vectors, multiplying them together, and adding by the multiplication of the y. By the way, this is just for 2 dimensions. If this was 3 dimensions, you would have a third term here where you would add the z component of A multiplied by the z component of B. But in 2 dimensions, we just have the x and y components that we are multiplying A component in the x direction multiplied by the B component in the x direction, and then add the A component in the y direction multiplied by the B component in the y direction. The other way in which you can do a dot product is you can take the magnitude of the first vector, multiply it by the magnitude of the second vector, and then account for the cosine of the angle between the two vectors. So we would let theta be the angle between the two vectors. That's the formulation I'm going to use for this work integral. So more specifically, what I'm going to do is I'm going to talk about an integral from 0 to d where I have some magnitude f, some magnitude dx, and the cosine of the angle between the two. In this problem, the displacement of the particle is going in the x direction, and the force being applied to this particle is also going in the x direction. And more specifically, the force is going to the right, which is positive. The displacement is going to the right, which is positive, which is to say this angle theta is 0 degrees. The displacement and the applied force are parallel to each other. And so when you have the cosine of 0 degrees, this term goes to unity. Cosine of 0 is equal to 1. This simplifies our integral such that now we have 0 to d. And remember, we have an expression for f that was equal to qx squared. And then the magnitude of some differential element dx is just the scalar of that. And q is a coefficient that does not vary as a function of x, which means that we can take the q out. So now we're going as a definite integral from 0 to d x squared dx. Now I'm going to actually compute the integration such that I have q, and then I'm going to have a 1/3 x cubed. You can imagine if I took the derivative of that, the 3 would come down, so 3 over 3 would be 1, and then it would go to x squared. So that's why I have the 1/3 x cubed. And that's going to be evaluated from d, or shall I say from starting at 0 to d. And so just to carry this out, this is going to be q times the quantity 1/3 d cubed minus 1/3 0 cubed. You can imagine 0 cubed makes that term vanish. And so this equals q over 3 d cubed. And that is going to be the answer for the expression that involves a distance d and some coefficient q that describes the work done by some variable force F that happens to be in the x direction and is parallel to the direction of the displacement. So just to review, if we've got an expression for our force as a function of position, then we can insert that into an integral. And since the work integral involves a dot product, we need to think about the angle between the applied force and the displacement. And since in this case the applied force and displacement were parallel, that meant that our cosine theta term goes to unity because the angle between the two vectors is 0. And I showed you how you can think of computing a dot product in two different ways, and for the purposes of our integral, it made sense to use the version of the dot product where you take the magnitude of one vector, multiply by the magnitude of the second vector, and multiply that by the cosine of the angle between the two. When I substitute the expression for the force as a function of x, I then get an integral where I'm looking at qx squared dx being integrated. The q is a constant, so it can come out of the integral. And then it's a straightforward integration of x squared dx to ultimately result in our final expression. And so this is the final answer you're looking for, q over 3 d cubed. And so that's how you solve for problem number 10 in problem set number 5.